In this lecture, we are going to build the data sheet of the telescopic OpAmp that we've been discussing so far. Before we do that, let us look at one or two more aspects of the telescopic OpAmp before we go further. The first point that we're going to learn is it is possible. So far, we have been building the we have been using the high swing version of the current mirror. It is of course possible to build the low swing current mirror. The biasing is just a little bit simpler. The low swing version would be as follows. So we are going to take this portion and create the low swing or the easier version of this. So that will look as follows. So we will take this OpAmp and instead of creating this feedback to create the high swing node, we will simply use two diode connected devices on the left hand side as the mirror device. So this will not require a separate VB5. We have seen what the value of VB5 should be in the current mirrors lecture. So as you can see, this requires one less bias voltage, but the voltage at this node will be higher than the original case, and therefore this swing is lower compared to the original version, compared to the left hand side figure. So that is something to keep in mind. It's just a little bit easier. Everything else is the same. Everything else is almost the same. There will be some small differences, but more or less they are the same circuit except for this particular biasing difference. Next, I will also point out that it is possible to build what is called a triple cascode amplifier. So similar to the telescopic amplifier with a single cascode device, it is also possible to add a double cascode or a triple cascode device. So you can add one more set of cascode devices on top of the original amplifier cascode to create this amplifier. So this would have a gain, as you might imagine, the gain would be of the order of GM/RDS the whole cubed. So this would give you even larger DC gain. However, if you had a load capacitance CL, it would turn out that the overall transconductance does not change, and the unity gain frequency omega u is still GM1 over CL. That does not change, and this only gives you better DC gain compared to the original circuit. Of course, now that you have added a extra set of two devices in series from VDD to ground, so this circuit is expected to have much lower swings. Of course, R out is much larger. Apart from this, you would also expect at low frequencies, you expect no additional noise from the new extra cascode devices. Finally, I want to point out, because this circuit has much lower swings, it is not very useful for low VDDs. So VDD less than maybe 2 or 3 volts. For VDD less than 2 or 3 volts, this circuit is not very useful. So you do not see it very often. Finally, even in older generation processes where you did have the supply headroom to use such circuits, there are some limitations. You can't just keep adding cascode devices, because at the end of the day, there are parasitic diodes, reverse bias diodes, hanging off the drains and sources of every transistor, and it would turn out that the impedance of those devices would limit the overall impedance at the output node. So I'll show them here. So these are the parasitic diodes, reverse bias diodes of of M5 and M6. So they will have some RD, they will have some dynamic resistance which will come in parallel with the cascode resistance. As you keep adding more cascodes, the value of RD does not change because each device has its own fixed parasitic reverse bias diode. Therefore, there is not much value to add a larger stack of devices. Next, I wanted to point out that it is possible to build the PMOS telescopic op-amp. Similar to the possibility of building a single stage op-amp with PMOS input stages, it is also possible to build a telescopic op-amp with a PMOS input stage because the signal characteristics of the op-amp is of the NMOS transistor and PMOS transistor are the same. Therefore, if you build a telescopic op-amp with PMOS transistors, you expect the signal characteristics to be the same, you expect the DC characteristics to be different. So we will draw the PMOS amplifier here. So and the input goes to the PMOS transistors shown here. I'll call them M1 and M2, and let us say this is the positive and this is the negative terminal of the op-amp, and the op-amp is biased with a current source of value 2I0, and as you can see, this is the cascode amplifier, and we'll call them M3 and M4, and M5, M6, M7 and M8 are the NMOS current mirrors. So let us appropriately add the feedback. So M5 and M7 will have a bias voltage VP5 applied to the gates. They are the cascode transistors, and the gates of M1, of M7 and M8 are biased using feedback. So to create a high swing current mirror, the output is of course taken from the drain of M6 and M4. Apart from this, the signal characteristics are the same. There is one point to remember. So you need larger PMOS transistors for the same GM. Therefore, you expect that the non-dominant poles and zeros to be closer compared to the earlier case. To be smaller, I mean closer into the origin. And therefore, for the same phase margin in unity gain, you expect the omega u to be smaller. Or rather, maybe I should put it in a different way, because we are comparing for the same GM, for the same omega u, expect the phase margin to be smaller. So, in other words, you will need to pull in the omega u. You need to reduce omega u to achieve the same phase margin. So that is another point. And finally, of course, the most important point of this is that the input common mode range of the PMOS version is different, because you expect the input of the PMOS device at a different bias voltage compared to the NMOS device, and that can easily be calculated for this particular circuit. So now we will take our high swing current mirror, the telescopic OpAmp with the high swing current mirror, and build the data sheet for that particular OpAmp. Now let us assume that the currents and sizes are known. So now we are in a position to build the data sheet. So the first characteristics that we are interested in is the DC gain. Even though I say DC gain, I want to re-emphasize that this is actually the low frequency gain and not the gain if you apply a DC voltage at the input. So of course you can apply an incremental DC voltage at the input and achieve the same DC gain. So the DC gain of the OpAmp is GM1 times R out, where R out is nothing but GM6 RDS6 times RDS8 in parallel with GM4 RDS4 times RDS2. So it has a very large output resistance. Number 2, the unity gain frequency omega u is GM1 by CL, where CL is the load capacitance that is being driven in feedback. Of course, the dominant pole omega d will be 1 over R out times CL, and as you can see, the dominant pole and the omega u are related through the DC gain of the amplifier. By writing this, we are assuming that the non-dominant poles occur at a much larger frequency compared to omega u. What about non-dominant poles and zeros? As we have seen, you expect this system to have a total of 6 poles, so and several zeros, because you have multiple paths. So there are several of them, several additional poles and zeros. And we'll point out that the first non-dominant pole is at node X, which is basically so the position of the pole is GM7 over Cx, where Cx is the total capacitance at node X to ground. The fourth parameter that we'll write is the input referred noise of the telescopic OpAmp. As we have seen, the input referred noise En squared has 2 components. You have the component from M1 and M2, you have the component from M7 and M8, and as we saw, the component from M3, M4, M5 and M6 do not appear as an input referred noise at low frequencies, because the gain or rather the path the current noise takes to the output is such that they get cancelled at the output short circuit mode. So the overall input referred noise voltage in squared is 16 kT by 3 GM1 times 1 plus GM7 over GM1. And as you can see now, we also know what to do to reduce noise. So to reduce noise, you need to increase GM1 as much as possible, and you need to decrease GM3 as much as possible. Now please note that increasing GM affects the signal, whereas GM3 is the this should be GM7. Since this is the telescopic op-amp, you are trying to decrease the GM of these two transistors and increase the GM of M1 and M2. Now it should be noted that M1 and M2 are part of the signal path, and the GM will affect this DC gain as well as the unity gain frequency. However, you notice that the value of GM of M7 and M8 do not directly affect the signal characteristics such as DC gain and unity gain frequency, and therefore it is possible to minimize the GM7 without affecting the signal too much. However, there is one catch. So if you decrease GM7, I0 remains the same. In such a situation, you will find that the VSD SAT of 7 and 8 increases, and this means the available headroom, in other words available output swing limits, are affected. So in other words, you are basically saying that the minimum voltage that M8 can have before it hits the edge of the triode region is getting larger and larger, because as you can see, for the same current I0, to decrease GM8 or GM7, you need to decrease the size of W over L. So I'll write that down in this manner. So W over L of 7 and 8 decreases and VD SAT increases. And this means the minute VSD SAT increases, the available output swing limits will definitely reduce. So that is something to keep in mind. There is a point beyond which you cannot reduce GM7 further. So next, we will look at the input referred offset. So as we saw, again this had two components, the input referred offset squared, which is the standard deviation of the input offset, had two components. The component from the input devices 1, 2 appears directly at the input, and the component from 7 and 8 appears at the input with a scaling factor GM7 over GM1 the whole square. So again, if you want to reduce the input referred offset voltage, you need to reduce the VT offset, VT mismatch between the input transistors. You also need to reduce GM7 over GM1. So you need to decrease GM7 over GM1. As you can see, decreasing this factor GM7 over GM1 would reduce both the input referred offset voltage and the input referred noise voltage. The next datasheet parameter we will look at is the slew rate of the op-amp. As we have seen, the positive and negative slew rate are both equal for this op-amp. And it is equal to 2I0 over CL. The input common mode range is the next quantity. We have seen that the minimum input common mode is achieved when M0 just hits the edge of triode region, and at that point the minimum input common mode range is VGS1 plus VDSat 0. So this is the minimum input common mode range, and if you were to start increasing the input common mode, eventually M1 and M2 will go into the triode region, and the edge of that region comes at a time when the gate of M1 goes larger than its drain by Vt. So the gate of the transistor is at VCM in. So that happens at VB3 minus VGS3. This is the drain of M1 plus VT1. So this is the input common mode range. Similarly, the output common mode range is as follows. The output common mode range, the maximum output common mode range in this particular situation is when M6 hits the edge of triode region, that is simply VB5 plus VT. It's simply VB5 plus VT5 or VT6. And the minimum input common mode range, minimum output common mode range happens when M4 hits the edge of triode region. That happens at a voltage of VB3 minus VT4.